this is how the data looks like. So this data is about the hair product, and this is the survey data for hair product. Okay, so we have here the questions in the survey data. So in the survey, so we have here the product quality, and for example, this is the technical support, advertising, salesmen, or things like that. Okay, so this is users' answers to these questions. Okay, and if you look at this data, there's this column named the satisfaction. This is the last column. Okay, so yeah, this is overall satisfaction, and all the other dimensions are about some details for the hair product. Okay, so yeah, we mainly use the detailed questions except for this overall satisfaction. Okay, so if you are using the regression model with this data set, this satisfaction would be the y variable. Okay, so the satisfaction would be the y variable, and all the other details for this hair product would be the x variable. Okay, so we are using this we are using this data for our factor analysis, but we will exclude this satisfaction dimension. Okay, so again, this would be the factor analysis input. This ID is again, this is an index value, so this is unique identifier for each consumers. Okay, so yeah, so we will not use this ID for the factor analysis because it's not gonna it's not meaningful. Okay, so before running any factor analysis model, let's take a look at some visualization for the data set. So this is a histogram and this is a box plot. Okay, so let's take a look at the histogram of the customer satisfaction variable. So yeah, if you look at this, this looks like approximately normal distribution, a little bit right skewed though. Okay, so yeah, a little bit right skewed, and looks like there's no outliers, so there's no extreme values. That's what we can see from the histogram. If you look at this box plot, we can see pretty similar trend. So this is there's no extreme values looks like, and the minimum values here is 5 and the maximum is 10. And yeah, so this is pretty yeah, so there looks like there's no outliers here, and just the similar trend in the histogram. So we can see this data is a little bit right skewed in the box plot. So these are the histograms for all the variables in the data set. So this is for the product quality, and this is for e-commerce or things like that. Okay, so this is the histogram, and yeah, looks like most of them are normally distributed. Okay, so yeah, no variable is heavily right skewed or the left skewed. The actual input for the factor analysis is correlation matrix. Okay, so you have to create the correlation matrix before running the factor analysis. Okay, so yeah, so this is how the correlation matrix looks like for the hair product data. Okay, I will skip all the mathematical representation for the correlation, but please make sure that you know the correlation is a statistical association and commonly refers to the degree to which a pair of variables are linearly related. Okay, yeah, so if you look at this correlation matrix, what we can see here is that there is a high correlation between the sales here. So where is sales image? So there is a sales image here, Salesforce image and the e-commerce, okay? And the correlation between those two is 0.79, okay, which is pretty high for the correlation. So we can see, we can find this kind of the trend in this correlation matrix. So based on the fact there's a high correlation between Salesforce imaging and the e-commerce, we can expect that those two variables may belong to one underlying factors in the factor analysis result. Okay, so yeah, so we can just quickly look at this kind of a trend here. Okay, so if you feed that correlation matrix that we saw in the previous slide, this is the output from the factor analysis. Okay, so this is the main factor analysis output that is called the factor loading matrix. Okay, so yeah, this is the main factor analysis output. Okay, so here we have 6 factors, so 6 underlying factors from the factor analysis, right? And our inputs, how many inputs do we have? We have 11 questions from the survey. Okay, so we have 11 questions from the survey. Okay, so how to read this result? Each value in this cell, so each value in this cell is called factor loadings. Okay, so the overall, the whole table is called the factor loading matrix, and the value in each cell is called the factor loading. Okay, so we have 6 times 11 factor loading values here. Let's look at the factor loading matrix more closely. So let's first look at the factor loadings for the product quality. Okay, yeah, so if you look at this, the factor loading values here, this is somewhat positive on the factor 4. So if you look at, so when you look at this factor loading matrix, we look both the magnitude and the signs, okay, positive or negative. Okay, so we look both the magnitude, the values, and the signs, which is a positive or negative. Okay, so yeah, so if you look at this product quality, it loads the factor loading, the factor loading values looks like this is somewhat positive on factor 4, because this is a positive value, and the magnitude is almost 0.5. Okay, so 0.45. So yeah, this is pretty significant. So we may expect that this product quality belong to factor 4. Okay, so yeah, so that's for the product quality. And how about the complaint resolution? What we can see here is, yeah, so if you look at this, the factor loading values, this one, the under the F1, under the F1, which is the factor loading value under F1 is 0.84, which is significant and high, and this is a positive value. So we can say that the complaint resolution loads heavily positive on factor 1. Okay, yeah, that's what we can see for the complaint resolution. And let's do this a couple of more things, a couple of more questions. How about the product line here? The product line, if you look at this factor loading values, right? So here under F1, this factor loading value is positive and significant. It's rather high. And what about the others? Under the F2, this is negative, and this is somewhat significant. So for the product line loads heavily positive on factor 1 here, and somewhat negative on the factor 2. Okay, and how about the delivery speed? If you look at the delivery speed, it loads heavily positive on factor 1. The value is 0.91. Okay, so yeah, this is have the positive on factor 1. Okay, so when you first get this the factor loading matrix from the factor analysis, yeah, this is how we read this the matrix. Okay, so we see both the signs and the magnitude of these factor loading values, and just roughly think that which variable, which x variable, so say which questions belong to which underlying factors. Then how to read these factor loading values in terms of the magnitude. There's a rule of thumb about the size of loading. Okay, so this is the rule of thumb. So the absolute value of the factor loading is if the absolute value of the factor loading is greater than 0.7, it is excellent. And if the factor loading absolute value of the factor loading is greater than 0.63, this is very good. And if it's greater than 0.5 of 0.55, then it's good. And if it's greater than 0.45, this is fair. And if it's less than 0.45, this is poor. Okay, so this is how we read this the factor loading values. So going back to this factor loading matrix, for example, this factor loading value under F1 for complaint resolution is the absolute value of this value is over 0.7, so this is excellent. And how about the product line? This is also over 0.7, so this is excellent as well. And how about this the value for the product quality under F2? This is the absolute value of this is 0.41, so this is yeah, this is less than 0.45, so this is considered poor. If you visualize the factor loading matrix and plot the factor 1 against factor 2, this is how the plot looks like. Okay, so this is factor 1 and this is factor 2. So just quickly going back to this factor loading matrix, this is a factor 1 and factor 2. Okay, so we visualize these two factors in this slide. Okay, so this is the visualization. So what we want to see here in this plot is which variables have high values in factor 1 and factor 2. Okay, so yeah, that's what we can see from this plot. Then how about for the factor 1? So what we can see here is that for example, we can identify the order and billing. There's some overlaps here, but there's order and bills. There's values. There is variables, order and billing, and the delivery speed. So those two variables are overlapped. So those are the two values, and there's a complaint resolution and the product lines. Okay, so we can identify that those four variables have high values for this factor 1. Okay, so yeah, so just so what are the factor 1 and factor 2? So we may roughly name the variables, the factors factor 1 and factor 2 in this slide, maybe, right? So which variables have the high values on factor 1? Again, these are the order and billing, delivery speed, product line, and complaint resolution. Okay, so just quickly going back to this the factor loading. So for this factor 1, the complaint resolution, the product line, the order and billing, and the delivery speed, those four variables have the significant and the positive values for this factor 1. Okay, so this is the same, this is similar what we saw in this the visualization. Okay, so yes, again, so the factor 1 is high on factor 1 are the order and billing, delivery speed, product line, and complaint resolution. Okay, so yeah, then then we can, based on these values, we can name this factor 1. Maybe we can name this factor the carrying functional aspect. So again, what we can do with this visualization is that we can figure which variables have high values on each factor, okay? Factor 1 and factor 2. And then we can roughly name the factor here, okay? So for example, for the factor 1, this is, we can name it carrying functional aspect, okay? Yeah, so this is, by the way, this is unrotated result, okay? This is unrotated, and we will talk about the rotations in the next slide. The rotation makes the result more interpretable, so each question loads more heavily on one factor, so the patterns are going to be more, the patterns are going to be clearer with this rotation method. The rotation is a transformation of the initial solution into a new solution, which is easier to interpret. Okay, so the result, so the rotation result again is that each question loads more heavily on one factor. Okay, so that makes the interpretation easier. So these are the plots of factor 1 against factor 2 before and after the rotation. Okay, so this is the unrotated plot and this is the rotated plot. Okay, so what we can see here is that there are less overlaps in this rotated plot. There's less overlap here and there's less, so there's overlap here and overlap here, but there are less overlaps in this new rotated plot. And we can also see that the variables are moved toward the extremes of each factor. So if you look at here, there's the tendency where these variables are the variables gather in the center, but those variables move to more extreme values in each factor. Okay, so that's what we can see. So we don't deal with any technical details about the rotation, and all we have to know here is that the usage of the rotation. So we use the rotation method for the factor analysis because it makes our interpretation for the factor analysis easier. So with this rotated plot, we can roughly think that which variable name, what names we will give for each factors. Okay, and there's no right or wrong answers for giving names. Again, like the cluster, this is the moment when you need to have your intuitions. Okay, so when you need to use your intuitions for giving names for these factors. Okay, so yeah, so if you look at this, this dimension for the factor 2, which variables have high values on this factor 2, e-commerce, sales, images, and advertising. So roughly those three variables have high values on this dimension, factor 2. So we may name it images. We may name this factor 2 images dimension. Okay, and how about the factor 1? If you look at this, the values here, looks like the delivery speed, complaint resolution, order, and billings. Those variables have high values on factor 1. Okay, so yeah, so it looks like this is about the functions. So we may name this variable, this factor 1 functions. Okay, so we have been covering several concepts or some technical stuffs for the factor analysis so far. So we have been covered factor loading metrics, rules of the sum for the size of factor loadings, the rotations, and how to name the factors. Okay, and how to name the factors, you have to use your intuitions based on the values, based on the factor loading values, and you can also use the plot, the visualization with the two factor dimensions. Okay, so those are the things that we have been covering, and in this slide I will talk about how important are factors. Okay, and the factor importance comes for free from loading matrix. Okay, so we can see the factor importance based on this factor loading matrix. Okay, and the factor eigenvalue, so I will introduce this the concept eigenvalues, this matrix eigenvalues, and eigenvalue. Based on this eigenvalue, we can see how important factors are. Okay, so this is the eigenvalue. And by the way, this matrix, this factor loading matrix is rotated. Okay, so this is the result after the rotation. So this is different from what we saw in this previous slide. So the previous factor loading matrix, this is unrotated, that was unrotated, and this matrix is now rotated. Okay, so how to get this eigenvalues for each factors then? Okay, so we will take a look at that eigenvalue, how to compute these eigenvalues for factor 1 and factor 2. And how to compute it, this is quite straightforward. Eigenvalue is the sum of squared values for factors. Okay, so this is how to compute the eigenvalue. So for example, eigenvalue for the factor 1, we square all the values under F1 and add the values. Okay, so for the eigenvalue 1, so we square all the values under F1, and if we add those values, then that will be the eigenvalue for the factor 1. And how about eigenvalue for factor 2? Again, we do the same thing. We square all the values under F2 and add those values. Then that will be the eigenvalue for F2, factor 2. Okay, so this is how we compute the eigenvalues. Then how to interpret those eigenvalues. The higher eigenvalue means more important factors. Okay, so for example, the eigenvalue 1 for the factor 1 is 2.7, and eigenvalue 2 for the factor 2 is 1.9, it's almost 2. The eigenvalue 1 is greater than eigenvalue 2, so the eigenvalue 1, so the factor 1 is more important factor than factor 2. Okay, and yeah, this eigenvalue can be used to determine how many factors we keep. So I will talk more about this in the following slides. So the idea here is that the important factors explain a lot of the variability of the data. So this is exactly the same logic as with the regressions R squared. So we can compute this the percentage of variance using this eigenvalue. Okay, so again, the important factors explain a lot of the variability of the data. So we so how to compute this, the proportion variance, which is the percent, which is the same to the percentage of variance. Okay, so how to compute it is that eigenvalue divided by the number of questions. Okay, so we have here for this hair product, we have 11 questions. Okay, so yeah, so just the formula is simple. This is just eigenvalue divided by the number of questions. So for example, for this first factor, the proportion variance can be computed like this, 2.7 over 11. Okay, 11 is again the number of questions. So we can say that the factor 1 explains 24.7% of the data. Okay, so this is the idea about the important factors explain a lot of variability of the data. Okay, and what about the factor 2? If you compute, so just going back here, if you compute the proportion variance using this formula, you can get this the 0.18. So again, factor 2 explains about 18% of the data. Okay, so yeah, so this is how to compute the proportion variance. Then what is the cumulative variance? Yeah, the idea is we just add up those factor, those proportion variance. Okay, so we start with the variance, proportion variance for the factor 1. So the cumulative variance is 0.247. And if you added those proportion variance for the factor 1 and factor 2, the cumulative variance would be 0.428. And if you add up those three proportion variance for factor 1 to 3, then it is 0.584. So this is the cumulative variance of this data. Okay, so yeah, so what we can see here is that we can interpret this result like top 3 factors explain 58.4% of the data, which is the cumulative variance up to factor 3. So how many factors to keep? Okay, so this is the similar question that we have in the cluster analysis. How many clusters do we have for the cluster analysis? Okay, so we have to decide how many factors to keep, and please record that the number of factors should be less than the number of questions. Okay, so we have here the 11 question, so the number of factors should be less than 11, because if it's over 11, there's it couldn't be 11, but if it's 11, the number of factors is 11, there's no reason for us to use this factor analysis. Okay, because one of the important reasons why we use this factor analysis is dimension reduction. Okay, so we want to reduce the number of items in the questions to the smaller set of factors. Okay, so that is the main reason why we are using this factor analysis. Okay, so yeah, so how many factors to keep is it's quite important decision that we have to make in the factor analysis, and there are several ways to decide the number of factors. And the first rule of thumb is called the Kaiser rule. So keep all factors with eigenvalues is over 1. So if we go back to this slide where there is eigenvalues here, and we can see that the eigenvalues for the factor 1, 2, 3, and all the way to the 6. And we can see that the eigenvalues 1, 2, 3, and 4, their eigenvalue is over 1. Okay, so based on the first rule of thumb, which is Kaiser rule, we will keep up to 4 factors. Okay, because those eigenvalues are over 1. Okay, so this is the first rule of thumb. The second rule of thumb is keep enough factors to explain 50% or over of the variance. So if we go back to this slide, you have to see this cumulative variance, okay? So yeah, up to factor 3, this is already over 50% of the variance. Factor 4, this is the over 70% or things like that, okay? And after factor 4, the variance is, the proportion variance is, it increases very slowly. So yeah, that's what we can see from this table. So maybe, or based on the second rule, we keep the variables, the factors up to 3 or 4 based on the second rule. So going back here, okay, so that's the second rule. So we keep enough factors to explain 50% or over of the variance. And this is the last one. This is closely related with this Kaiser rule. So we look for the elbow or the script plot. So this is a similar idea that we did in the factor analysis. So we use this elbow plot for deciding the number of clusters, okay? So yeah, we use this discrete plot for the factors as well, factor analysis as well. But in this case, this x-axis is factors, number of factors, and the y-axis is eigenvalue, okay? And again, this rule is somehow similar to the Kaiser rule, because we mainly see the eigenvalue to decide the number of factors, okay? So when you create this the script plot, we can see that there's a number of factors here, and this is the eigenvalue, okay? So just if you look at this plot, we want to keep the factors with eigenvalues is over 1. So if you look at this number 4, factor number 4, this is slightly over, its eigenvalue is slightly over 1, okay? But after the 5 or 6, the eigenvalues of this factor is less than 1, so we may want to keep the factors up to factor 4. So the result from this script plot is consistent with what we saw in this table here. So I just copied this eigenvalue from the previous slide. So this is the eigenvalue for factor 1, and this is factor 2, and up to factor 4, the eigenvalue is over 1, but after factor 5, the eigenvalue is less than 1, and this is consistent with the result, what we see from this script plot. So next thing, what we want to do in the factor analysis is naming the factors. And we touched on this earlier in this lecture, okay? So I will just briefly explain how to do that again. So yeah, so this is the plot for this factor 1 and factor 2, okay? So we plot these factor loading values for the first factor and the second factors, okay? And we can do, you can do this for the third factors and the fourth factors as well. But here we just deal with this the factor loadings for the first factor and the second factor, and how to name that. As I mentioned in the previous slide, we see the variables that have high values on each factor, okay? So how about for the factor 1 then? So yeah, we already named them for the factor 2. The name is we named it images, and we named the factor 1 functions, okay? So and these decisions are based on the variables that have high values on each dimension, okay? So for example, for this x dimension, which for this factor 1 dimension, which variables have high values? The delivery speed complaint resolution, order and billings, those variables have high values on this factor 1, so we named it functions. Okay, and how about for the factor 2, which variables have high values on the factor 2? The sales force imaging, e-commerce, or the advertising, those variables have high values on this factor 2, so we named it images. Okay, yeah, so this is how we name it. And again, there's no right or wrong for naming the factors. This is the moment where you need to use your intuitions again. So for example, for deciding the number of factors, this is more about, so we are using more technical we are using techniques to decide the number of factors. Okay, but for naming, you have to use your intuition. Okay, but based on the result from the data. So we have been dealing with some concepts or the technical details of the factor analysis so far, and this is how we apply this factor analysis in the real world. Okay, so this is the real world practices. So we will focus on the following applications with this factor analysis. Summarize underlying factors driving data. So this is related with the factor analysis itself and naming the variables. Okay, and the simplify surveys. So we can simplify the result. We can simplify the survey. We can remove some of the questions from the survey using the factor analysis, and I will show you how to do that in the following slides. And we can create the managerial composite scores, and I will show you this later as well. And we can generate the perceptual map using the factor analysis. So first application is summarizing underlying factors. Okay, so let's get names for the main factors. So we first ran the factor analysis with the 6 variable. Okay, and we took a look the eigenvalues and the script plot and all the stuffs, and decide to have 4 factors. So we want to keep 4 factors for this hair product data. Okay, and then rerun the model with 4 factors. Okay, with using that the rotated method. So we are using, so for the final interpretation and the final result, we are using the rotated method. Okay, specifically the varimax rotation for the factor analysis. So instead of using the initial factor analysis result, we are using the varimax rotation for the final result and for the final interpretation. Okay, so we rerun the model with 4 factors using that the varimax rotation, and this is the result. Okay, so this is the result. So yeah, so what we can do here is that we can name those factors here using these factor loading values. Okay, so for example, for the first one, again, which variables have the high values for the factor 1, the complaint resolution, the product line maybe, and order and billing, delivery speed, so we name it functions. How about factor 2, the e-commerce, the sales images, those values, or advertising, those 3 factors have high values for this factor 2, so we name it images. And how about factor 3, which variables have high values for the factor 3, technical support, and the warranty and claims, so I name it technique and warranty. And how about factor 4, the product quality, product lines, yeah, those values have a high, those variables have high values for the factor 4, so I name it product line. So another application of this factor analysis is simplification of the survey. So when you want to simplify your survey, you can use the factor analysis. Okay, and how to do that? The communality is one of the ways we determine which questions we drop from the survey, okay? And what is communality? Communality is the percent of variation in question explained by factors. And the low communality means the factor is, the items or the questions are not categorizable. So this is the low communality, means uncategorizable, and this is a similar logic to the extremely low R-squared. So that means this variable or this question is not explained by important factors. So we decide to drop the questions or the variable, okay? So low communality means uncategorizable. And then what is the low communality? Ideally, we want to keep the questions whose communality is over 0.5, okay? So this is the communality rule for simplifying surveys. So from R, we can get this communality values. So how to get these values? So this is the code for the factor analysis, and I will show you how to run this code later in the R session, but this is the code for the factor analysis, okay? And if you run this code, one of the results from the factor analysis is uniqueness. So this is the one kind of metric that we can get from this factor analysis, okay? And the communality is 1 minus this uniqueness value, okay? So 1 minus uniqueness. So for example, for this product quality, the communality of a product quality is 1 minus 0.44, okay, which is 0.56. So 0.56, this is the communality. So based on the communality rules, should we keep this variable or should we drop this variable? Yeah, we have to keep this variable because its communality is product quality. The communality of this product quality is over 0.5. Then how about the others? If you look at this e-commerce or technical support, its communality values are over 0.5 as well. So we may want to keep those variable. Or how about the advertising? Its communality value is less than 0.5, okay? So maybe we consider to drop this variable from our survey, right? So these are the rule of sums for simplifying survey, okay? And there are several rules here, and first is the communality rule that I just talked in the previous slide. So if the communality of a certain variable is less than 0.5, we may consider dropping the variable from the survey, okay? And how about the second rule, the size of main loading? If the size of main loading, its absolute value is greater than 0.4, then we may want to keep that variable. If it's less than, the absolute value is less than 0.4, we may want to consider dropping the variable from the survey, okay? So yeah, there's no right example for this one, but for example, there's a certain variable here, and those loading values, factor loading values here are all less than 0.4, then we may consider dropping the variable from the survey, okay? And how about the third rule, meaning of items? So practically, we have to consider the meaning of the item, okay? If the item doesn't mean it's not meaningful in the survey, we may want to consider dropping the variable. And the first one is the number of items already in the factor. So if the number of items, for the certain factor is over 5, then we can be more selective. So there's no right example for this one because the number of items for the factor 1 is 3 and number of items for factor 2 is 3. So there's no factors whose number of item is over 5 here. But again, if the number of items in the factor is over 5, you can be more selective, okay? And how about the next one? The final rule of thumb is you want to consider the number of questions per factor, okay? So we want bare minimum of 2 or 3 questions per factor, okay? So just simplifying survey, you may want to consider the more than one rule of thumb to decide which variables you want to drop or which variables you want to keep. Okay, so let's move on to another example for the factor analysis. Okay, so I will use the toothpaste examples for another factor analysis. So this is the data. So this is toothpaste data. So we have only six variables here, and this is survey data again. So this is a survey for the toothpaste product. Okay, and our question in the survey, the number of questions are 6, and we are asking about if this toothpaste prevents the cavity or the shiny teeth, strengthen the gums, if it's fresh, decay, and attractive, okay? And this is the survey data, so the users or consumers rate for this individual characteristics of the toothpaste, okay? And it looks like it is measured on a scale of 1 to 10, okay? So yeah, this is how the data looks like. So again, the main input for the factor analysis is correlation matrix, okay? So correlation matrix is the input for the factor analysis. So first you gather this data from the survey, and then you have to convert that the raw data into the correlation matrix, okay? Yeah, so we know what the correlation matrix is. So the diagonal line, we find that the correlation between the prevent cavity and the prevent cavity, so those are the same variable. So we find that the correlation between this same variable is 1. So all these values in this diagonal line is 1, okay? So that's what we first can see from the correlation matrix. And then which variables have the high correlations? For example, here the prevent cavity and the strength gum. This is the correlation is over 8. So I'm sorry, this is over 0.87. So yeah, the correlation between the prevent cavity and the strength gums is pretty high. And what about the preventive cavity and the decay? This one is also very high. And the strengthened gum and the decay, those are pretty high correlation, okay? So this is pretty high correlation. So yeah, we can see that, and we may expect that those variables belong to one factor. So here we simplify the factor analysis procedure. So we directly go to this script plot to decide the number of factors, okay? And again, the axis is the number of factors, and the y-axis is the eigenvalue, okay? And there are several rules to decide the number of factors. We can use the Kaiser rule, where we decide the number of factors based on the eigenvalue, okay? If the factor's eigenvalue is over 1, then we will use up to that number of factors. So we will have that number of factors in our factor analysis, okay? So this is the script plot, and this is very close to the Kaiser rule. So this is the script plot for the toothpaste data, okay? So what we can see here is that we can see that the up to 2 factors, its eigenvalue is over 1, okay? 1 is over 2.5, and the factor 2 is over is between 2 and 2.5. So we know that factor 1 and factor 2, those eigenvalues are over 1, okay? And how about factor 3? This is eigenvalue is less than 1. So based on the Kaiser rule or the script plot, we decide to have 2 factors for our factor analysis, okay? So we have 2 factors for our factor analysis. Okay, so this is the result from R, okay? So this is the comment for the factor analysis in R. So we feed our data set here, and we decide that the number of factors equals 2. So you have to know, so before running this comment, you have to know how many factors you're gonna use for the analysis. And then we will use this rotation method, the Varimax, okay? So we specify the rotation method. So the factor loading matrix is the table after this Varimax rotation is applied, okay? So yeah, so this is the factor loading matrix after being after this the Varimax rotation is applied to, okay? So this is the factor loading matrix here. So we want to interpret that the names of the factors and which item belongs to which factor, okay? So yeah, so this is the main table from the factor loading factor analysis in R, okay? So yeah, just quickly take a look at this the factor loading matrix. Looks like it is quite simple. This is quite clear, so we can instantly know that those 3 factors, the first 3 items belong to factor 1, okay? Its factor loading values are all high, so it's almost 0.9 or over 0.9, okay? So we see that those 3 items belong to factor 1, and those 3 items, the last 3 items belong to factor 2 because its factor loading values are high, okay? This is very high for the factor 2, so we see that those values that belong to factor 2. And based on the factor loading guidelines that we saw in the previous lecture, all the factor loading values are excellent because its absolute value is over 0.7, okay? Yeah, so that's what we can see, and again, this is very clear because we use this Varimax rotation method. So the patterns is clearer because the variables move to the extreme values for each factors, okay? So yeah, so this is very clear. So we know that which item belongs to which factor from this factor loading matrix, okay? And another output from this factor analysis in R, this shows that the eigenvalues that we saw in the previous slide, and proportion variance and the cumulative variance, okay? So this is the eigenvalue. So based on the Kaiser rule, the eigenvalues is pretty high for the factor 1 and factor 2 as well. This is over 1, so based on the Kaiser rule, we will keep those two factors, okay? So because this eigenvalue is over 1. Okay, and what about this proportion variance? Proportion variance, what we can see from the proportion variance is that we see that how much of the variance is explained by each factors, okay? So how to interpret this one? So we can say that the 42% of that the items, 42% of the data variance in the data is explained by factor 1, okay? So 42% of the variance in the data is explained by factor 1, and 32% of the variance in the data is explained by factor 2, okay? So this is what we can see. So proportion variance, we can see that how much variance in the data is explained by each factor. So the cumulative variance, we can use this to decide the number of factors as well, and how to compute this cumulative variance. If you add those two proportion variances for the factor 1 and factor 2, and that's gonna be the cumulative variance up to factor 2, okay? So this is cumulative variance. So if the cumulative variance is 50% and over, then you will use, you will keep the variance, you will keep the factors around that, okay? So yeah, it looks good because this is the cumulative variance is over 50%, okay? This is 74%, okay? And yes, so it's just going back to this eigenvalue. The eigenvalue, based on the eigenvalue, we decide how important factors are. So it looks like the factor 1 is the most important, and the factor 2 is the second most important, okay? Yeah, so this is how we see this eigenvalue, proportion variance, and cumulative variance, okay? Yeah, so now we looked at the factor loading matrix and these eigenvalues and the variances. And the last piece of information we can see in this result is this uniqueness. So uniqueness, so we can compute that the communality using this uniqueness. So 1 minus uniqueness equals the communality, right? So how to use the communality rule? When we use this communality rule, so when you decide when you simplify the survey, so when you decide which variable, which questions you're gonna drop from your survey, you may want to use this communality, okay? So again, the communality is if the communality for the certain variable is over 5, then we want to keep that variable, okay? So yeah, just take a look at that, the communality here, 1 minus 0.06, this is definitely over 0.5, so it's a communality. The communality for the prevent cavity is over 5, so we want to keep this variable. And how about the second variable here, the shiny teeth, 1 minus 0.44, that is over 0.5, so its communality is over 5, so we want to keep this variable as well. The strength gum, its communality is also 0.5 because 1 minus 0.17 is over 0.5, so we want to keep this variable as well. And the fresh, its communality is definitely over 0.5, okay, so we will keep this one as well. And for the rest two variables, the communality for those variables are over 0.5 as well, so we want to keep these variables too, okay? So yeah, so from this communality analysis, we concluded that we want to keep all these variables, all these questions in the survey, okay? Yes, that's what we can see from this result.